these members in the truss, there are two force members. What that means is the force is only acting, the force can only act along the member. All right? These are all called two force members. So the forces they are along the member, which means what that means to you and me is to solve and find the force in member BH, you can analyze the joint B or H. You can isolate and analyze either of the joints at the ends of the same member. And if you do it correctly, you will get the same answer, no matter which end joint you analyze. All right? In this case, as I told you before, it's a T-section. Definitely apply the method of joints to point H. And what do we mean by that? Well, you isolate the joint H, and here's on slide 8, I'm showing that. You isolate the joint H and draw the free body diagram. Draw the free body diagram, and this is at the bottom, this is the free body diagram of joint H. What you have to do when you isolate it, guys, you cut the member. Cut the member here, here, and here. All right? And when you cut a member, guys, you make, in my opinion, what you do, you make the internal force become exposed. That's why when we cut HG, for example, I replace it with the internal force HG. Same thing with BH and the same thing with AH. All right? Now, that is the free body diagram for the joint H. Now, once you have the free body diagram, what you need to do is apply the equations of equilibrium. And as Stephen told us earlier, there are two equations of equilibrium at each joint. Those are summation of forces in the x direction and summation of forces in the y direction. Now pay attention. If you sum the forces in the x direction at the joint H, what do you get? You would get FHG is equal to FAH. What are you solving for? We're solving for FBH. All right? So the unknown would not even show up in the summation of forces in the x direction. However, if you sum the forces in the y direction, as we have done here, assuming y going to the top is positive, what do you get? FBH positive. Is there anything else in the y direction at the joint H? The answer is no. Therefore, FBH would have to be equal to 0. Several of you, including Donald, identified this and said earlier that FBH is 0. In fact, if you are able to recognize that by inspection, that's fine. But I just showed you so you can see. This is called a 0 member. All right. Some of you may ask, say, well, all right, if BH is, let's look at the truss up here. If BH, this member is a 0 member, which means it's not capable of resisting any loads or carrying any loads, well, then what happens to that 300-pound force that's acting in the vertical direction at B? Well, please pay attention. That 300-pound force will be reacted upon by the Y component of these inclined members, AB and BG. All right, let's move on. Next, I want you to help me find the force in member BC. Now, BC, remember, the first thing is I want you to take a look and decide which method should you use. Remember, Ian told us there are two methods, method of joints and method of sections. Here, BC is a member in the middle, and I would recommend we use the method of sections to analyze this. All right, very good. And Fami is saying method of sections. That's fine. Sandra is method of sections. Let's do it. When we use the method of sections, what is it that we do? Well, basically, we cut the truss at a given section. Here, that would be the section that I would use. In other words, I'm going to cut through BC, then the diagonal and the bottom chord. Let's take a look at the next slide. All right, so there it is. Please take a look at the top, and this is the section. It's a vertical section, so basically, since we are looking for the force in member BC, BC should be one of the members that we cut. All right. So there you go. That is the section that we do. So what do? First, we cut the truss. The next thing that we need to do is the following. We need to draw the free body diagram, the complete free body diagram, either to the right or to the left of the section. And that you could see down here, guys. You can see the free body diagram. In this case, I'm using the free body diagram to the right of the cut. It really doesn't matter whether you choose to use the one to the right of the cut or the left of the cut. If you do it correctly, you will find the right answers. However, there are a couple of things I need to tell you. In this case, since I'm using the segment of the truss to the right of the cut, there are a few things that you need to pay attention to. First of all, the members that you cut, you can't just go through life cutting truss members and just leave them hanging. Whenever you cut a member, the internal force in that member becomes exposed, as I told you before. So I cut BC, I'm showing the force in BC. All right? Which other ones did I cut? BG. All right? Look at what I did. I'm showing the internal force in BG as such. And then also HG, there it is. All right? Now, what about the external forces? Here, and this is very important, especially those of you who have not done many of these kinds of problems since you left college. What about the external loads? Well, the 400 pound, for example, is acting at the point C. So here's what you need to do. Is the point C part of this free body diagram? And the answer is yes, it is. Then you will include that force. All right? Now, as opposed to, you see up here, it's pale. You don't really see it very well right now, but that says 300 pounds. There is a force of 300 pounds there. All right? So do we include that? Well, no, because that acts at the point B, and the point B is not part of this right-hand side of this truss. All right? So the 300-pound force at the point B does not. We don't need to include that. All right. What do we do next? Well, remember, we want to find the force in member BC. So this is the unknown. What do we need to do? Who can tell me what's the easiest way to find the force in member BC? Who can tell me? Okay. Matthew, Andrew, Jonathan, hold on. Ryan, Black and Veach, several people are saying right the moment about the point G. Now, we have some other suggestions also, but please pay very close attention. If we write the moment about the point G, those of you who are saying writing the moment about the point G is the quickest way, you are correct. All right? So writing the moment about the point G is indeed correct. And if we write the moment about the point G and solve for the reaction at BC, that would be the quickest way to solve for that problem. Now, let me explain why. Because, in fact, that's what I did here. Look at the equation up here. I summed the moments about the point G, set it equal to 0. The reason that's the quickest way and the best way to solve this problem, guys, is because, look, how many unknowns do we have? Well, we have BC. This is unknown. The force in BG is unknown, so is HG. But if we write the moment about the point G, two of the unknowns disappear because BG and HG both go through the point G. Therefore, they will not show up in this equation moment about the point G. Therefore, look at it. That equation is just one equation, one unknown. Now, you also see RR. That's a reaction at the right support, and that I didn't show you, but you should be able to solve that independent of this. All right. So RR, even though I show it as an unknown, but that's a reaction at the support E that you should be able to do it by equilibrium. So reaction at R is or reaction at E is 275. Substitute that in there, and then we get this. The answer is what? The answer becomes 733. All right? Does everybody follow? You solve for FBC, and it comes out to be 733 pounds. Does everybody follow that or accept that the force in member BC is indeed 733 pounds? Now, there is one other thing here, and that is it says it's in compression. Now, how do we decide whether it's compression or tension? Remember I told you earlier that you also need to learn how to decide whether a force is in or a member is in tension or in compression. Brian, in order to find this 275 pounds, Brian is asking, how do I get the 275 pounds? For this truss, this is what you need to do. Please write the equations of equilibrium about the point A. Sum the moments about the point A, and the only unknown would be RR, and you get 275. Do me a favor, Brian. Do that and see if you have any problems with that. Please send me an email, and I'll be able to do that. All right. Fami asked why RR has negative. I think what you're talking about is this here. Why is that negative? That's the direction. That's the direction, because you see, Fami, we are assuming that clockwise is positive, all right, and that RR about the point G in the direction that is shown will cause a counterclockwise moment. That's why it's negative, all right? Again, if you have any questions with that, please let me know by email. But this is important, guys. I need to cover this before we move on. How do we decide the force in member BC is in compression and not tension? All right? Here's what we do. In order to do that, you have to decide whether the internal force in the member, let's talk about BC. The internal force in the member, if the force pulls away from the joint, pay attention. If the internal force pulls away from the joint, that member is in tension. All right? Now, if the internal force pushes towards the joint, then the member would be in compression. All right? Now, when we analyze these members, for example, BC, we don't really know whether the internal force is pushing towards the joint or pulling. What we do, we make an assumption. And if you recall, when I told you to use the method of sections and use these three forces, BC, BG, and HG, what is my assumption here? I assume you have to make an assumption towards about the direction of the internal force. I have assumed all three to be pulling away from the joint. Does everybody see that? Just look at the arrowhead. All right. So, in other words, I've assumed all of these three are in tension. All right. Now, when I analyze the beam, now pay attention.